We begin the study of kinematics. Kinematics. Essentially, we are measuring the movement. Kin refers to moving or movement of things, and matics is a sort of a suffix, I guess you could say, that indicates some kind of measurement of kinematics. Well, you think of mathematics, right? Measuring and using numbers to describe. So kinematics is basically how things move. That's what we're really talking about here. And it's part of a sort of a bigger unit or a bigger area of study in physics called mechanics. The other part is something called dynamics, which is when you combine dynamics, which is what makes things move, and you combine that with kinematics, you get the entire sort of study of something called mechanics. So here we are studying this, kinematics and how things move. All right, well, let's first of all talk about some very simple concepts. Let's say that we are standing here and nothing is happening. Well, if nothing is happening, there's nothing to measure, and it's not very exciting. But if we decide to walk over here, then we've effectively changed where we are. What we've done here is we've changed our position. If you change the position of something, essentially you move it from one place to another. Another word that we use when we say we've moved something is we say that we have displaced it. To displace means to move from one place to another. So a displacing or a displacement is what describes how we move from one place to another. And of course, we can describe this in two ways. We can describe it simply with a number and a unit of measure. So we could measure how many meters that it was, if those were markations of meters. It looks like about 6 meters, and we could describe this as a distance of 6 meters. So this is what we would call the distance, 6 meters of movement. But we can actually add some more information. Now that you know a little bit about what a vector is, we can add a direction to the distance as well. And we can take this 6 meters and we could describe it in a different way. I'll change colors just to emphasize that. We could say that if this movement was towards the, let's say it's towards the right, we could call this 6 meters right. And by adding that direction, we have now created a more complex number with two properties, a number that tells us how much, but also which way. And that's, of course, what we call a vector. And the other one, the distance, was called the scalar, right? It doesn't have any idea or any connotation of the direction. And of course, we sometimes use different names for concepts when we have a vector instead of a scalar. So instead of the distance, what we do is we borrow this word over here that means to move things, and we call this the displacement. And so that's what we mean by displacement. We mean something that has been moved. And we're measuring the displacement from where you began. That's kind of an important thing to remember early on. It sounds like it's pretty standard, but there will be times when it will be a little bit odd. When we talk about displacement, we're talking about a sort of a measurement from a starting position and then how far away you are from that starting position and in which direction you have moved. So 6 meters to the right. If I had moved this way, that might be 3 meters to the left. I could also move 2 meters up or down or hither or yonder or east or west or whatever words we want to use to indicate the direction. Later, we will discuss how we indicate the direction using mathematical language instead of English words. But for now, we're just going to write our vectors with a number, the magnitude part, and then square brackets indicating the directional idea. Okay, so displacement is a measure of how something is moved. It's a measure of the change in our position. And of course, we can do all kinds of things to describe this. We can describe it using graphs and numbers and things, as we'll learn in a minute. But let's think about one more thing that has to happen here. If you're going to move from one place to another, there's something else that has to sort of change. There's another changing thing besides just your position. And of course, that is the time that it takes for you to walk from one place to another. So there's really two things changing. There's your position and there's time. And then, of course, if we compare those two things and how they change, let's compare. Now remember, mathematics is a language. And the way we say something compared to something else in mathematics is by using a fraction. A compared to B. That's what that actually means in English. We say things like A divided by B, or the ratio of A to B, or we even look at that and say it's a fraction, A is a fraction of B. But really what that means is A compared to B in some way. So that's how we say the words compared to. So in English, if we want to say the displacement, all right, the displacement, which is a fancy way of saying the change in position, the change in where you're located, right? And I want to use the word change because it's important. The change in where you're located. And if we compare that to the change in the time it takes, how much the time has changed, we get a very interesting thing. If you were to run those 6 meters to the right, and there was only a little wee bit of time that changed, you would say that you ran very fast. But if you sort of crawled those 6 meters to the right and lots of time changed, you would say that you crawled very slowly. And so what we see here is this comparison actually represents something. When we compare how our position changes with the change in the time, we get something, and we call it, I'll squeeze it in here, the velocity. Now, velocity might be better known to you as speed, and we kind of use those words interchangeably in physics when we get going, but we really shouldn't, because there is a small and rather important difference. Velocity is the vector where you have a speed and a direction, and then speed itself is just how fast you're going without referring to any particular direction. It's the scalar. So remember the difference between vectors and scalars. Okay, so that's going to give us some kind of indication as to how fast we're going when we make this comparison. Now, we can write this with symbols rather than with a bunch of words. We can translate this even further into more mathematical language by using symbols. The change in position is usually the displacement, and so we can use a D to represent that. And the change in time, well, what we can do, of course, is use the little change symbol. This little delta symbol means the change, right? And you learned about this little symbol in your grade 9 and 10 math classes. It's the change in the displacement or position compared to the change in the time, and that would equal the velocity. We have what we call a little formula here. Now, in mathematical language, and as you move on in physics, you're going to see that we don't always use the same letters for things. Typically, changes in position are referred to as an S rather than a D. And I think that's because the D has a lot of very special calculus meaning. And so we don't use the D, they use S for position. So when you get into your grade 12 calculus class, you'll see that they would write delta S over delta T. is equal to the velocity. But it really doesn't matter as long as everybody's on the same page. And for some reason, early physics textbooks prefer to use the D. I guess they figure it's easier for kids to remember because D in displacement, right? S doesn't really look like it belongs. So where'd you get the S from, you know? But anyway, that's just the quirks of math. So we have this interesting little formula, and it basically is a relationship. It's a very particular kind of relationship because it's a comparison with time. Whenever you compare something to the time it takes, you're doing something very special. What you're describing is the rate at which it happens. The rate at which it happens. Let me write that all down here. So another way of talking about velocity or speed is by saying the rate at which something happens. And of course, rate is essentially how fast or how slow. And so now we have a very interesting little thing showing up here where all the things you learned in grade 9 and 10 suddenly sort of flash back. If something is a rate at which it happens, we can describe that rate. We can describe it with a graph. So let's go up to our little picture here. In fact, let me draw it again. I'll draw the little man over here again. And we're going to walk this way. And we're going to go 6 meters. And we're going to walk to the right. Okay. Well, let's define this. What we have to do is we have to have a sort of a measuring starting point. When you measure how far you go, there has to be a sort of a zero. And usually we use 0 to represent our initial condition or our original situation, right? Our initial position. So if we call this 0, then the 6, this would be 6, right? 6 meters away if we measured that with our measuring tape. And since we measured it towards the right, we have the vector 6 meters right to represent our change in position. Now let's think about a graph. If we take a graph and we graph D on this side, and we graph time like this along the x-axis, you'll notice I'm only drawing 2 of the 4 quadrants. And that's because over here on this side of the graph, these would be places where time had a negative value. And negative time is not really that meaningful in describing things that are happening. So we tend to ignore that part of the graph. We don't worry about it because it's really not going to tell us anything useful. Okay, so now what we have to do is we have to figure out how to plot this on the graph. Well, if this is our 0, our initial position, the place, now remember, we're plotting only the D right now. We're plotting the displacement. It's tempting to think, well, if the picture goes to the right, then I should be drawing a line on the graph going to the right. But that's not the case, okay? The picture might go to the right, but the graph is not a picture. It's a representation. So what we have to think about is when we're moving like this, we're moving towards the positive direction, right? To the right is positive. So if we're looking at a line that's now up and down, then positive is in the upward direction. So we have to start here, which is what we call our D1, our initial position, and we have to go up to the 6, which we'll put up here, our D2, which is our second position, D2. And so what we say is we're going to go from D1 to D2. Now, if there was no time, we would just draw a line straight up this graph on the axis. But we also have to remember at the same time this is happening, we also have at the very same spot here a T1, an initial time, which is usually also 0. And there's going to be a time 2. Time has to change. So we have 2 different times, the time when we start and the time when we finish. And when we combine these 2 things together, we go up and sideways at the same time. Simultaneously, we trace out a line that goes like this. And that line will line up precisely with this mark and this mark down here. And this line then, this blue line, represents the motion of the person who went 6 meters to the right. And of course, we can put the numbers on the graph if we want, but it's better sometimes not to put in numbers. It's better just to use the letters because these could be any numbers. I could have went 10 meters. Maybe I went to the left, right? If I'd gone to the left, my line would have went down this way towards the negative d numbers. So we can see how the graph can show us all kinds of different things. Now, here's what I wanted to show you. I want you to be aware of this. On a graph, there is a way in math you learned that was sort of an indication of how fast the graph was going up or down, how fast it was changing. We called it the slope of the graph, remember? From grade 9 and 10, the slope of the graph. If you change rapidly, you get a steep line. If you change slowly, you get a narrow, a shallow sort of slow sloping line. And the way you calculate slope in math is, remember, it's the change in the y-axis compared to the change in the x. And of course, this is the change in the y-axis on my graph, but I'm not calling it y, am I? I'm calling it d, so that is the change in d, the change in displacement or position. And then down here is the change in my time, or the change in the x, but I'm calling it t, so that becomes change in t for me. So this is my change in d, and this is the change in the time, how much it's changed. And of course, the way you get that is by looking at the graph and figuring out how long the line is. Now, the way you find out how long lines are is by measuring them or by describing them like this. Delta D would be the second D, take away the first D, D2 minus D1. And then down here, let me slide over here. This would be T2 minus T1. And so in math class, that's why we wrote this delta D, delta T. That's why the next line that you wrote when solving for slopes was to write D2 minus D1, or you might have written Y2 minus Y1, right? And when we start at 0, it makes everything simple, but you don't have to start at 0, okay? Let's just explore why this is true, why this works, because we often learn math without really understanding what's going on. Okay, well, let's say I have a line. Now, if I were to go to here, that was 6, then we would just look at the line if that was 0 and we'd say, well, it's 6, right? But you could also move 6 by starting here at the number 4 and going all the way up to 10. That's still moving 6. And so it doesn't matter what you call your starting point. So here, you would have to figure out that this is 6 from here to here. You would have to go, well, you're at 10, and you'd have to take away the 4. See, you'd have to go the D2 minus the D1, the second position, take away the first position. And then you would realize that you moved 6. And you're doing the same thing on the other side. It's just you're doing D2 minus D1, but your D1 is a 0. 6 minus 0 is 6. So you're mentally doing the same thing. But it's so easy to forget that's what we're doing. It's so easy to forget that we're actually performing a little subtraction when we do this. And so that's why we use that expression. Because you don't have to start at 0. You can start at 4. There are reasons why you might want to start at 4. We'll talk about that later. Okay, so that brings us back to, let me just erase some of this stuff that I've drawn here and get rid of this for now. And now we have this little expression that we have developed. And we have the slope of the line, right? But if you'll notice, the slope of the line, which is delta D over delta T, right here, is just a comparison of the change in position and the change in time. It's exactly the same as this, which means the slope of this graph is telling us what the speed or the velocity is. So we have this idea that velocity is the changing d compared to the changing t. And that is the same as saying the rate of change of position or displacement. Okay? But the displacement is the change in position. So let's say it's the rate of change of position. of where you are, which means it's how fast you change your position, which is equal to the slope on what we'll call the displacement time graph. We drew a graph there, and the axes were displacement and time, right up here, displacement and time. And so we have all of this now that we can use. And so we see there's a relationship between time and your position and how fast you go. And this relationship is very, very important. Now, let's play a couple of games with this. Let's take this interesting rate of change of position, which is what tells us what velocity is, and let's do some little calculations. Let me redraw the movement from 0 to 6. This time I'll put the numbers in. And let's imagine that we go this far in, I'm going to say 1, 2, 3 seconds. So the time is going to change by 3 seconds, but the position is going to change by 1, 2, 3, 4, 5, 6 meters. Okay? And it doesn't matter when you draw a graph if your scales are different like this. What matters are the numbers that anchor everything onto the graph. Okay, let's draw the line. Well, if we want to take our displacement and go from this point up to this point, but at the same time, we have to imagine the time going from this point to this point, then what we have to do is go on an angle like this and get this particular line. And of course, it would have to line up with the 6 right there, so we can put these little guidelines in to show that it lines up. We don't have a grid to show us, right? Okay. Now, let's put in numbers for our time as well. We said it was going to be 3. So obviously this is 0, right? We're doing the 0 here. So when we use 0 as a starting point, it simplifies the equation. We can describe the slope of this line, right? Or the slope of the line, which is equal to delta y, or delta d in this case. And we don't use x and y, we're using d and t. So it just turns into this instead of delta y over delta x. This equals d2 minus d1, and this equals t2 minus t1. And if we look at the picture, we have remember this is the D2 up above, and the D1 is the 0. And this is the T2 right here, and T1 is the 0. So what happens is we get this. Remember that the slope, another word for slope, is the velocity. So I'll just write V instead of writing slope. And then it's D2 minus 0 over T2 minus 0, because the initial values of both D and T are 0. And when we do this, then, it's very easy. D2 becomes the number that describes the change in position. It's changing by 6, because 6 minus 0 is 6. So we can sort of simplify this by writing just d over t. If we imagine that we're starting at 0, and the d2, the d now just represents going up to the red arrow, or the red dot, sorry, and the t represents going to the green dot, and we get this little shortcut, v equals d over t. But we have to remember that the d and the t represent changes, right? Changes. And then what happens is if we multiply both sides of this equation by t, we get vt equals d, right? Remember, you can multiply this and this by anything you want, as long as you do it the same to both sides. And if we just write that in the mirror, we get this little equation, which is a very common way, a very common shortcut way of writing this equation right here. But it only works when you start at 0. It only really works when both D1 and T1 are zeros. But because that's often, it's a good shortcut. And this might be a little kind of relationship that you might remember seeing You might have, in grade 7 or something, have seen this and realized that distance equals speed times time. Of course, now we realize if we use vectors, it's displacement equals velocity times time, and the directions are important. But it just shows you how we can arrive at this little shortcut using all of this sort of graphical interpretation of the rate of change of our position. And that gives us velocity. Okay, so that's about as far as we'll go on this video. Maybe I could just finish this off, right? We could actually calculate something. If I were to take this little expression and just, rather than go through all of this, I can use this other little shortcut that I have here, d equals vt. And I can figure something out because the d is how far we go up the axis on the d. Well, that was the d2, that was the 6. So we went 6, right, to the right. And then the t was 3. The d was 3. So this would be a v multiplied by a 3. And then, of course, we can solve the equation. If we divide both sides by 3, then we end up isolating the v. And that tells us that 2 is the v. The velocity is 2. And what would it be? Well, there would be a unit, right? The unit for velocity is, because it's a comparison, it's a sort of a fraction unit. It's the distance unit, in this case meters, compared to the time unit, which is seconds. And so we would say that the velocity here is 2 meters per second. And what that indicates is that you must have covered 2 meters in every second. And if we look at the picture, and I just get yet another color on top of this, if you follow this line, this purple line now that I'm drawing, you can see that at 1 second here, when we get to the 1 second mark, we've traveled 2 on the distance or displacement axis. And then if we go another second up here, look, we've traveled 2 more. We're at 4. And then we traveled another 2. So every one of these little seconds, we've gone 2 up until we get to 6. And that's what the velocity means, 2 meters per second. And that's how slope works. It's the comparison of going up on the graph as opposed to going sideways. And that's how we can deal with velocity. Now, the unit could be any distance. It could be kilometers per hour. It could be inches per day. As long as the top unit is some kind of displacement measurement, like meters or kilometers or miles or inches or furlongs or fathoms, and as long as the bottom is some kind of time, like hours, minutes, seconds, days, years, fortnights, right, which is not a video game. It's actually a measure of 2 weeks' time. But most of you know it as a video game, I'm sure. But a fortnight could be the measurement for the bottom of this. Typically, though, we have standardized units. We'll get to that later, and we use meters and seconds most of the time. So that's kind of how we deal with displacement and the changing of something's position. We can draw it on a displacement time graph, and we can calculate the slope, which represents the rate of change of the displacement or the position, and we call that the velocity. And we'll stop there for now.